So today I started with my session with the magnetics. Okay, so what is the magnetics? I know it's a very basic idea. So it's a basic electrical knowledge. All of you are aware about that. What the magnetic circuit? What is the basic idea of the magnetics? So our to discuss about the for the subject is quite it's quite different. Basically, if you see that in any of the switching converters, okay, normally any of the switching converter, you can observe that there is some inductors, okay, there is some energy storing elements like inductors, okay, capacitor, okay, you in single word you can say like that, filter inductor, filter capacitors, okay, lot of energy storing elements are there. So that inductor, if you see the switching frequency, okay, if you see the switching frequency of your switching converter, it is more or less beyond 50 kilohertz. Okay, so normal ferromagnetic material, if we are going to use normal ferromagnetic material, then what will be the problem? The main problem is that saturation problem. Frequency for additional power losses. So different process problems are there. Okay, if you there is some direct um, effects of high frequency operations in the magnetic material. Okay, so that's why the selection of the magnetic material, okay, the selection of the magnetics is most important in the designing of the switching converter. Basically, end of the day, we have to design the switching converters as per our application. Okay, so which application you are using? Okay, so as per their application, how much ripple frequency you are expecting from the inductor current range. Okay, how much ripple voltage you are expecting from the output side. So for the voltage ripple, you have to select the rating of the you have to select the compatible rating of the capacitor. But same thing also happen for input current ripple. Okay, so mitigate to minimize the input current ripple, also you have to select the inductor values. Okay, basically that inductor is normal. If you consider the buck converter, the boost converter, you know, you can see the or buck boost converter, there is a filter inductor. Okay, that inductor is behaves like a energy storing element. Okay, as well as sometimes it having some effect on the filtering. So some special type of converter like flyweight converter, in that case you can say like that it is transformer inductor. Okay, so it having different property. That inductor having different property. It behaves like a transformer as well as energy storing element. Normally transformer is not energy storing element. Okay, it is transforming the energy from LT side to HT side, or you can say like that, or HT side to LT side, means you can say like that in single way, primary side to secondary side. That in case of private converter, that we are using that inductor, that inductor is known as the transformer inductor. Okay, means it's behaves like a transformer as well as energy storing element. The special type of inductors are there. So selection of the important issue. That should be with the high frequency operations. Okay, it should be working with the good efficiency in the high frequency. Okay, you can understand that buck converter, boost converter is also working in the 50 hertz, 500 hertz, 5 kilohertz, 50 kilohertz, 1000, 100 hertz, 100 kilohertz. All the way it will be work. Basically, it is that gain. In steady state, it's the ratio of the duty. Its voltage gain is the in the function of the duty. You can say like that your buck converter, it can be worked at 50 hertz also. Okay, but it is independent of that function. It is independent of the frequency. If you see that relations, okay, that output voltage by input voltage, that relations gives you some gives it having some relation. The output by input equal to 1 by b, like that. Okay, so and that is independent of the switching frequency. Okay, but why we are making it more? Why we are selecting the switching frequency in higher end? Okay, basic motivation is that If you increase the switching frequency, then two things are there. Number one thing is that the sizing of the energy storing elements, okay, it will be reduced. Okay, the sizing of the inductor means that XL inductive reactance is directly proportional to the switching frequency, that X. Okay, if you increase the switching frequency, the size of the inductor will be less. Okay, in case of capacitor, more or less you can see 1 by XC. Okay, XC equal to what, 1 by omega C, you can say like that. What omega equal to 2 pi A. Increasing of N equal to XC will be high, but sizing of the capacitor, okay, sizing of the capacitor will be less. The energy storing element sizing will be less, increasing of the switching frequency. That is one thing. Another point is that efficiency. Okay, efficiency. Okay, so you know that buck converter also working in 50 hertz, 500 hertz, 100 hertz, 1 kilohertz, 5 kilohertz, 50 kilohertz, 100 kilohertz. So which one will be more suitable? So if you check the efficiency, okay, so you can see that if you increasing the frequency level, so definitely that efficiency is increased. The switch off on frequency. So normal ferromagnetic material if you are using. So if there is a problem of saturation, there is a problem of huge coil loss. Okay, so the humming effects. Okay, basically if you use the laminated core, that the soft iron laminated core. So is it possible to working at 100 kilohertz? No, it is not possible. So you have to select the magnetic material that is capable enough to handling with that 50 kilohertz and beyond that one. Okay, that's why we can switch the concept in the ferrite magnetic core. Okay, normally we are making that ferrite core. So in that case, you know that if you go through the one subject in your UG level, that is called machine design. Okay, if it is there, I don't know in current curriculum it is there in your syllabus or not. I don't remember. But when I was in BTech, means UG level, so one subject was there, machine design. Okay, so in my UG classes at that courses we are designing different calculations. So there was a written examination. Okay, so how to calculate the transformer, calculate the synchronous machine. Different machines are there. So what will be the tentative number of windings? Okay, what will be the gauge of the winding? Okay, what is your window factor? Winding. Window size, okay, bobbin size, that could be calculated. Same thing also happened here. What will be the type of the core? It is E core. It is what kinds of core is there? It is E core or EI core. Okay, so if E cores are there, so how it will be look like that? So is there any lamination? So how it will be practically looking that E core? So how to wind up that cores? Everything. Okay, those are working on that machine designing. So that course is very interesting. Okay, the topic was very interesting, but that knowledge is important for designing the magnetics. Basically, if you see the magnetics, that inductors are there. Okay, normally inductor or the transformer are there. Okay, for some of the switching converter, that transformer is important. Na? So high frequency like isolate the power converter, push pull converter, then flywave converter. Okay, so all are the examples of transformerized switch mode power converters. Okay, so in that case, the transformer also be there. Basically, that switch is in your primary side, and transformer is isolating the primary side to the secondary side. So there is a problem of the core saturation. So okay, it's a special type of transformer you have to be designed. Okay, so special type means only you are changing the material of the core. Okay. So some data sheets also available in internet that for small different companies are there. They are normally manufacturing the core of the switch mode power converters. Okay, there are ring type core, bar type core, also E core, EI core. Different types of cores are available. Okay, if you come to my campus, so I have in my lab I have different types of code. If possible, I can also show you. Okay, so there are also another element of the bobbin. Okay, bobbin means where you are wind up the conductor. Okay, so bobbins are there, and if you are wind up the conductor, so how much area is covered? Okay, that also is important. Okay, so covering of the area. So if all the then there is a problem insulation. So okay, what type of conductors you have to use? that should be insulated. It is called enamel core conductor. Okay, means that conductors, copper conductors are not in there in nature. Okay, there is some coating, enamel coating is there. Okay, so like your when you are designing any machine, so laminated E core is there. Okay, means very thin with okay very thin cross sectional area of soft iron cores are there that look like a E type E. Okay, so now if you are designing that core of that machines, okay, so you have to immerse them in the varnish. Okay, varnish. I think you are heard about the term varnish. Okay, so it is providing you that insulation between individual sheet of that core. Okay, so same kinds of thing for conductor. Okay, that we are using for designing that inductor conductors. Okay, so that should be enameled. Okay, it should be the enamel. Okay, otherwise they will be shorted. Okay, the selection of the magnetics is important. I think we are able to understand what is the basic motivations for the magnetics. So today I will give some very basics about idea about the magnetics that we have already gone to in your first year level. Okay, means your UG courses. Still some recap is required. Okay, so only few slides are there. So for the recap portions, okay, then in my next class, means tomorrow morning again I will take one class. At that class I will discuss about some example of inductor. Okay, so how it will look like that. Okay, so then I can comment the question. So I think you know about the basic ideas. So I am not giving more time, okay, on that discussion, but I will discuss some basics. Okay. So in the magnetics, what are the most important portion? That is basic magnetics theory, filter inductor design, and transformer design. So first portion is the basic magnetic theory, means Ampere's circuit law, Ampere's law, Lenz law, Faraday's law. Okay, then if there is some air gap, so what will be the process? We are using KVL, KCL. So we are using the KCL. Okay, so that portion will be discussed in the basic magnetic theory. Then filter inductor design means that if you are in any of the converter, okay, any of the converters, so you are using the inductor, no? So if inductors are there, so definitely if inductors are there, so definitely, so what will be the number of turns? Okay, what will be the cross sectional area, or the you can say like the gauge factor. Okay, what will be the gauge factor of the conductors? Okay, so if the conductors are there, so how much number of turn will be there? Okay, so what will be the critical value of the inductor? Okay, so if there is some impurities, how to get that impurities? Okay, so capacitor, if there is some capacitor, so how do you see capacitance? So ESR value, so you have to follow the data sheet also. So you are not able to preparing the code. You have to procure it from the any of the store. Okay, so if you have that model number, so you can search it in the in the Google. Okay, so you will get the data sheet of that in of the code. Okay, so you can understand what is the maximum flux density of the code. Okay, what is the total, you know now B equal to mu H. Okay, so that amount of what is the flux intensity, maximum flux intensity. Okay, that maximum flux intensity also be directly proportional to the NI. Okay, means how much current it can be tolerate. Okay, so that all the parameters are related to each other, and current density also. Okay, so you have to download the data sheet, and you can understand that for the specific code, what is the specifications, okay, of individual code. After that, you have to implement them. Okay, so first you have to select that code and that number. Okay, so to select the code means the material of the code also be changing. Okay, for 500 kilohertz, the material of the core is totally different. The shape and size of the core is totally different. Okay, with the 50 kilowatt core. Okay, so right now that megahertz range switching converters are used by using SIC device, by using GAN device. Okay, so in that case, special type of core you have to use. So what will be the type of core? Okay, is it ring type core, okay, or toroid shape? Is it toroid shape or bar shape, or is it transformer is looking like that? So you have to select it. Okay, that's why that is important, the selection of the filter inductor design and the transformer design. Okay, I think all of you will motivation. So very basic review of the magnetic basic relation. So you know the Faraday's laws. Okay, so that B omega T BT, it is BT means flux density. Okay, so phi by A. Phi by A means flux per unit area. Phi T equals to what? It is your lines of force, means flux line. Okay. Another one is that in Faraday's law means it responsible for induce some voltage. Okay, na? So the turning is there. So if you back a flux is there, definitely induce voltage. And Lenz's law calls that your cause always that effects always counter its cause. Okay, that's why that induced EMF always countered its cause. Okay, the concept of the back EMF. Okay, so that EMF induced due to the terminal voltage of the machines. Okay, terminal voltage of the machines means motor normally. Okay, the back EMF is observed in the DC motor, not in DC generator. EMF is induced in DC generator, but it is not called back EMF. Okay, only it is observable in the DC motor. So who is responsible? Who is the cause? Basically armature current. So from where you are getting the armature current, that is your terminal voltage VP. And what is your induced EMF in transfer in motor? It is EB, back EMF. Okay, so EB means back EMF. So definitely who is cause? DT is cause and who is effect? Okay, so that is EB means back EMF means induced EMF is effect. So both are countering each other. Okay. That's why that minus sign is there in case of motor. Okay. So same thing, it's also happened for the Faraday's law and the Lenz's law. Same thing also happened for your transformer also. That terminal voltage, primary voltage also be there, and you are getting the reversing. Okay, means minus y axis you are getting primary. That means induced EMF. So then the Lenz's laws are there. So due to Lenz's law, it will be again minus E1. So it will be again come towards your plus y-axis. Okay, like that. So Faraday's law is the basic concept. Then core characteristics means HTFT means how much force MMF. Okay, so how much MMF is HT means how much maximum current. So it is Faraday's law. Okay, and it is from Ampere's law. So you know that one. So Ampere's circuital law. So how much current will be there? H equal to current intensity, flux intensity. So flux intensity directly proportional to your current flowing through the magnetic material. Okay, current flowing through the conductors surrounded in the magnetic material. Okay, so if you increase the strength of the current, so how it will be magnetized? So in the core, okay, ferromagnetic core, so lot of polar magnets. Okay, means lot of polar magnets are there. Initially, they are not aligned. Okay, so they are not aligned. Okay, so if you give some external magnetic field, okay, so in the orientation of the lines of force, the polar magnets are aligned. Okay. So if you increase the strength of the magnetic field, how do you increase the strength of the magnetic field? Ni means number of turns. You can increase the number of turns. Another thing, you can increase the current intensity. Okay. If you increase the current intensity, so the magnetic field strength will be high, and that may cause for more alignment of that current. Okay, of that polar magnets. Okay, so that may cause for what? That may cause the electromagnets. Okay, so how much it will be increased? So it's having some limitation. So fixed number of polar magnets are there. Okay, so if you try to move, get more polar magnets, it's not possible. For individual magnetic material, it's having some fixed number of polar magnets. Okay, or you can say like that. Sorry, molecular magnet, not polar magnet, molecular magnet. Okay. So a fixed number of molecular magnets. So it will be aligned. Okay. So in intensity of the magnetic field, that means HP. Okay, it's directly proportional to I. But it's having some linear region. After that, it will be saturated. Okay. So it is the force. Okay, that is external force that is responsible for alignment of the magnetic molecular magnet. Okay, so four characteristics. So total these questions are the four characteristics. Your four characteristics also decided the characteristics, the values of the B, H, phi, and the external magnetic field F. Okay. So it is your terminal characteristics means electrical characteristics. So VT means you are giving electrical voltage and IQ is electrical current. So these portion are the electrical characteristics and right side portions are the magnetic characteristics. Okay. Is my slide is visible from your side?
Yes, sir.
Okay, okay. So now we can discuss about some basic quantities. So basic quantities means in magnetic quantities you know about that value mmf equal to what? In EMF equal to V equal to I into R means current into sorry V equal to I into R means reluctance into current. Okay, in case of MMF it will be a resistance into current in electrical circuit. In magnetic circuit it will be reluctance that is proportional to the reluctance and your flux. Okay, so if the reluctance is high, so definitely countering of the field will be high. Okay, so your flux line also been counted. Okay, the flow of the flux line also been counted. Okay, that's the problem. Okay, so in magnetic quantity, you can see what is the function of the reluctance. It is L, length of the field. Length of the conductors and magnetic field H. So you can say like the mmf is equal to H into L. Okay, H is intensity, L is the length of the conductor. So it is flowing from x1 to x2. So how much force will be observed? That is in your magnetic circuit. The same thing also happened in the electrical circuit. The length of conductor is L. Okay, so voltage equal to E into L. Okay, so induced EMF into length. If here that force is it is EMF means it is EMF. Voltage means it is EMF in electrical circuit. In MMF in magnetic circuit. Okay. So H into L, here it is E into L. Same thing, flux density over here. So it is phi and B. Phi is the lines of force, B is the flux density. So B equal to phi by A. If your surface is S and area is AC, then it will be coming that B equal to phi by AC. Same thing also happened in electrical quantity. Current is your main quantity, then current density. So J equal to I by A. Okay. J is the current density. Okay. Then see the motive force. So directly x1 to x2. Okay, so if you know that individual portion, it is h into dl. So if that point is moving from x1 to x2, that point is there here. Okay, x1 to h2, that magnetic field point it is moving. So how much value of the force, mmf force will be there? It will be x integration from x1 to x2, h into dl. Okay. So magnetomotive force A between point x1 and x2 is related to the magnetic field H according to means additions. Okay, so x1 to x2 means addition of different values. Okay, finally we will get that one. Okay. So example of the uniform magnetic field of the magnitude of H. Okay. Then analogous to the electrical field, strain E which induce the voltage EMF V. So definitely same thing also happen for electrical field. Okay, magnetic field and electrical field. Okay. Flux density V and the total flux phi. Okay. So again you need to calculate the flux density. You have the expression of the flux density V equal to phi by A. Okay. So for the small cross sectional area V equal to what, phi by dA. Okay. So you have to, if you want to calculate the phi, so you have to integrate that value. So integrate surface S. Okay, that is V dot d delta I. Okay, the total magnetic flux phi is passing through the surface of area AC is related to the flux density B according to the functions. Okay, that all are the concept from the UG level concept. Okay, I'm just recapping that value, recapping that portion. So that you can directly make an integration, you will get the total flux. Example, the uniform flux density of the magnitude I equal to B into AC. AC is the total cross sectional area. Okay. Then you know the Faraday's law. So lines of force are passing through the conductor. Okay. So cutting, you can say like that, induced. So potential. So voltage induced. Okay. EMF induced to the path. Okay. If the lines of force or flux are cutting through that path. Okay. So the voltage V is induced in a loop of wire by changing in the total flux phi t interior of the loop. According to the Faraday's expression, will be Vt equal to d phi t dt. Okay, flux line phi t equal to what? It will be integrations of that phi t equal to integration of V into dt. Okay, so for the uniform flux distribution, phi t equal to Vt into AC, and hence you can replace that value IT you have replaced, that is AC, it is replaced here. So it is replaced here AC into VT. Okay, so AC is the constant one, so it will be coming out. So VT equal to AC dVT dt. Okay, so you know that basic concept of Faraday's law, so you can get that induced EMF. Okay, the conductors are there. Okay, rate of change of cutoff flux may cause for induced EMF. Okay, the rate of change of cutoff flux cause for induced EMF. That is your Faraday's law. Okay, so induced EMF is here. That is VT. Okay. So Lenz's law means again Faraday's law means as per the Faraday's law, you know that in EMF will be induced. In Lenz's law, you can get the polarity of the induced. So that polarity will be countered of your cause. Okay, so the effect will be countered. Effect will be countered of your cause. Okay, the voltage Vt induced by the changing of flux phi t. Okay, from the Faraday's law is of the polarity that tends to drive a current through the loop to counteract the flux change. Okay. So if you directly, so there is some basic example in Faraday's law. Okay, when we are was in +2 level. Okay, so there is some voltmeter. Okay, connected across a coil. Okay, now we are having one bar magnet. So now we are passing the bar magnet to the coil. Okay, then what happens? You can see the voltmeter is deflected, means that some of the amount of EMF is induced, that's why voltmeter is deflected. Okay, so now what is the polarity? Polarity will be reversed, means countering the effects of that cause. Okay. The example is it is a shorted loop of wire. Okay, it is a shorted loop of wire. It is induced current. That induced current is flowing over there. So flux is phi t. It is the first cause. Okay, that is flux is responsible for induced current. Okay, that circulating part means eddy current part. Okay, so that current will be developed due to the flux phi t. Okay, so now what happens again? That current is circulating, means that may cause the magnetic field. Okay, so you can get some right hand thumb rule. So what is the direction of the magnetic field? First flux line is there, that is responsible for cutoff flux, that may cause for induced current. Okay, you get the current direction. Okay, so you get the current directions. Okay, from left hand from screw rule. Okay, from the screw rule you are getting the current direction. Means corkscrew rule. Okay, so you get the current direction. After getting the current direction, so now that current also responsible for induced. That current also responsible for magnetic field. Okay, if you see the magnetic field from the right hand thumb rule, then you can see that induced EMF direction is countering of your main field flux. Okay, I think all flux is the corkscrew rule, you can get the induced current direction. Okay, or you can use the Fleming's rule. Okay, so you will get the induced current direction. After getting the induced current direction, induced current is responsible for magnetic field. Okay, so then you can use the right hand thumb rule. Then you are getting the magnetic field direction. Okay, if you have the induced current, so you will get the magnetic current direction, induced flux direction by using right hand thumb rule. So you will get that induced flux is countering the main field current that you have obtained, that you have given past. Okay, it is shorted loop. So that's why you just prove that coils are always countered by the effect. Okay, so a short circuited loop of wire is there, changing of flux phi t induces a voltage Vt around the loop. Okay, this voltage command divided by the impedance of the loop conductor leads to current IT. This current induces a flux phi t which tend to oppose the change of phi t. Okay, I think you can understand, also can understand what is the idea about the Lenz's law. Then Ampere's law. Simple thing, current circuital law, you know that Ampere's law means net MMF, closed path, or in the. So total MMF is what? Total MMF around the closed path is equal to the total current passing through the interior of the path. So You know that's the concept of the Ampere circuitous line. So you know that symbol. It is the closed integral symbol. Okay, the closed integral symbol, and H into dl. So MMF I am telling you na H into L. So small part you have considered small L, that is dl. The total current passing through the interior of the car. Okay. The example is that magnetic core, the wire carrying current IT passes through the core window. Okay. Illustrated, the path follows the magnetic flux lines around the interior of core. For uniform magnetic field, the same HT integral MMF HT So FT equal to HT equal to I. Okay, so it is a magnetic field. Okay. Ampere's law discussion. So what we can discuss from that law? So relate the magnetic field is to be upon your current stream, but there is some limitations. Okay, there is some linear zone. After that, it will be saturated. After that, it is not increased as much you are wanting. Okay. We can give the winding currents as sources of MMF. The previous example, the total MMF around FT equal to HT now equal to the winding of the MMF IT. Okay, HT is a function of IT, that's why you can replace that one N into I. So FT MMF equal to NI into L. Okay, NIL, nil, you know that one. The total MMF around the closed loop according to the winding current MMF is zero. As per the laws of energy conservation, the total MMF around the closed loop definitely will be zero, means incoming always be equal to the output. Otherwise, it is not valid the laws of energy conservation. So, okay. Then core material. So you know, I think all of you are aware about the BH loop. Okay, what is hysteresis loop? So that's the very important concept. Okay, for the selection of the ferromagnetic material. So hysteresis loop is that if you increase the value of H, here you can see, if you increase the intensity of the current, okay, increase the amplitude of the current, okay, of the ferromagnetic core. Okay, so you can see that H also be increased. You can see linearly increase that B means I increase means that is responsible for increase the lines of force, means your I also be increased. Okay. So increasing of the phi, okay, how much it will be increased? Definitely that molecular magnets, all the molecular magnets is aligned as per the lines of force or lines of MMF, means field MMF. Okay. So it will be aligned. Then what happens? There, if you increase beyond that value, so there is no molecular MMF, sorry, molecular magnet. After that, it will be saturated. Okay, so after that, it will be saturated. You are trying to reduce the current value. Okay, first you are increasing the current value, or you are increasing the intensity H value. Okay, H is directly proportional to current. Okay, so current first you are increasing, then current you are going to be reduced. Then what happens? As per the properties of the magnetic material, it is not following the same path. It will follow the different path. Okay. Again, it will be come back. So making it zero. So you have to give some negative current. Means current in the reverse direction. Okay. So after that, it will that value also increase in the negative side. Okay. Then again you are making it zero. So again you increase the value of current. So it will be positive side. So finally we will get that type of structure. Okay. So in between one is decreasing part. So all the time it is not following that way. So spontaneous magnetism if you changing, so all that path also will change. Okay. But for the single cycle, you can see the structure is highly non-linear. Okay, and that area is then in between to increasing part and the decreasing part. That area is means wasting the energy. Energy is wasted. Okay, that energy is wasted in between the area. So it is called hysteresis loss. That is responsible. That energy loss is responsible for hysteresis loss. Okay, that hysteresis loss consists of two things. One is called core loss component. Okay, so that core loss component is there. Okay, so core loss component is hysteresis loss plus eddy current loss. Okay. So why that loss is there? Okay, you have to know about the philosophy. Why that loss is there? Okay, basically, what is our cases? So you know about the reactive power. Okay, reactive power means what? That amount of power is maintaining the voltage source. Okay, that is the maintaining the voltage profile of the system. Okay, reactive power is the soul of the any of the system. Okay, so it is always maintaining the voltage, but some of the energy is utilized to making the molecular units. Hysteresis low. Okay, so that energy is reflected in this way. Okay, so that is called hysteresis loss. Okay, so how do you reduce that energy? Sorry, how do you reduce that loss? By only possible is that selection of the magnetic material. Okay, so which type of ferromagnetic core you are using in your switching converter? Okay, so that totally depends upon that selection of the material. Okay, if you use the ferromagnetic material, you can see the area. Definitely, hysteresis loss is always be there. Okay, in any of the application, any of the converter, but how much less area is there, that is most important issue. So you can see in ferromagnetic core the area is quite less, that's why you are using that type of area, sorry, you are using that type of material. So ferromagnetic material for switching converter. Okay, so your main motivation is to reduce the area of hysteresis. The free space means if there is no magnetic, so directly it is linear. Zero permeability, the free space is 4 pi into 10 to the power minus 7 Henry per meter. Okay. And highly nonlinear means is the real time factor. Okay. The hysteresis and the saturation. Now the piecewise linear modeling for the core material characteristics. No hysteresis of the saturation. If it is ideal case. Okay. So if you increase that path, so the ideal cases definitely there will be no hysteresis. But in case of saturations means non-linearity also be there. Okay, that is your BSAT. So when you are download that, when you are able to download that data sheet of the core material, okay, data sheet of the core material. So there they have mentioned BSAT means flux density saturation when it will be saturated. So you have to select the value of BSAT, okay, in higher range. Other what happens? Increase value, it reach that BSAT value. Okay, that you have to be selected. So if you increase the more current region, so what happen? Your code will be saturated and it will be in the linear zone of operation. It is not acting as a linear circuit. Then it will be act as a non-linear path. Okay, that's why your BSAT value should be high. Okay, if you are using high current applications, means you are using, there is some input current na, in your converter, switching converter, some input current will be there, some inductor current will be there. How much value of that maximum current will be there? Okay, that will be designed by your side na. So after getting that amount of current, then you have to select the core. Okay, so select the core. So and for the selection of the core, you have to understand that which code you are going to be picked. Okay, which code you are going to be picked. Okay, basically that current is less, then what happens if you are using that type of code, so the B saturation will be very less. Okay, that's why you have to select such amount of code, you have to select such ferrite code which having more B saturation. Okay, so typical B saturation is that ferrite code is 0.3 to 0.5 Tesla. Okay, so that's the reason. Okay, so powdered iron, it is 0.5 to 1 Tesla and 1 to 2 Tesla for the iron instrument, iron laminations. Okay, but in your cases you are using ferrite code, that Tesla value is quite less and that is sufficient enough. Okay. So units are there. What are the most important units? Okay, units are the magnetic quantity. So B means flux density. It is unit is Tesla. H equal to ampere per meter. Pi is Weber. Okay, all are the SI unit. In case or SI unit. Okay, so unnaturalized cages means relations. Relations are there. Mu RH, gauge, ORH, Maxwell. That all are other conventions also be there. Okay, so the Tesla and gauge, that concept means relation, correlations. Okay, wasted. Okay, then Weber and Maxwell, the relationship are there. Then simple inductor. Okay, so we are much more focused about the simple inductor. So you know the Faraday's laws for the each turns of wire, where the d turn t equal to d d phi t dt. You know that one. Okay, current I is there. Okay, so number of turns in. Okay, so if the voltage appear across the coil, so current is flowing through that path. So flux line phi will be developed, and it is your core area AC. Okay, core permeability is your mu. So total winding voltage is there, Vt equal to N into V turn. So V turn equal to d phi dt. We know that Faraday's law, induced EMF equal to rate of change of cutoff flux. Rate of change of cutoff flux is d phi dt. Expressed in terms of the average flux density, Vt equal to phi t by AC. Okay, Vt equal to N AC dVt dt. Okay, that's the relation you are getting directly. Replace that value. Vt equal to what? Phi equal to B into A. Okay, Vt into A. See, that is previous we were getting the relation. Okay. The inductive example for the Ampere's law. Okay, so choose the closed path. That total path is closed. Okay, and magnetic flux line length is Ln. Okay, magnetic flux line length. Okay, the following the advantage of the magnetic field line around the interior of the core length of the path is called the mean magnetic path. Okay, that is mean magnetic path. So enter the path, the flux line is not flowing. Okay, it will flow only the least magnetic path. Okay, so mean magnetic path definitely less than your total path. Okay, for the uniform magnetic field strength, the HT, the core MMF around the path is equals to H into Lm. Okay, H into Lm is there. So winding contain n turns of wire. Okay, each carrying current IP. Okay, so in terms of wire is there and carrying the current IP. The net current passing through the path of interior, that means through the core window. So core window is there is NIT. NI means your ampere. Okay. Ampere's law, we have that H T Lm equal to NI. So you know that value B value equal to plus B saturation minus B saturation. Both of the saturation is important because of the hysteresis nature. Okay, so which amount of positive current, which amount of negative intensity. Intensity, intensity. That values are important for the saturation. That I have already discussed. The selection of the core materials. Okay. So which type of core material is available? First you need to check and their applications. After that you can go for it. Find the winding current at the onset of the saturation. Substitute I equal to I sat, H equal to B sat by A. You know that mu H, na, B equal to mu H. So B sat also be there. If we replace that one, so what is your intensity? H. That I equal to I sat. So you can replace that value. So you get that relationship. Okay, I sat equal to, you know that B sat Ln whole divided by mu into N. Okay. You know na, formula is same. Formula equal to what? B equal to mu H. Okay. Again H equal to what? N into I. H equal to N into I. You just replace that one. I sat into N. Okay. And that portion is B sat by mu. It is already there. And Lm will also be multiplied. Basically that multiplications of Ni na, we are calculating the MMF. Lm mean magnetic flux, but that also been multiplied over here. So electrical terminals and what was your voltage, induced voltage as per the Faraday's law? You are getting that formula. Previously it was already discussed that Vt expression HTLM equal to N into I, that is your MMF. So that expression also be there for flux density. B sat mu H. Okay, normally it is V equal to mu H and it is minus B sat. Okay, when that H is greater equal to B sat by mu. Okay, that H mod H less than B sat by mu, it is minus B sat for H less equal to B sat by mu. Okay, eliminate that B and H and solve the relation between V and I. For mod I less than equal to I saturation. So okay, Vt equal to that mu M AC HT by dt. Okay, HT dt. So you can get the expressions, direct expression we are getting over here. Okay, that Vt expressions. Then inductor expressions is there. That all are in the subjects of field theory. Okay, that are also in your BTech subjects. Okay, field theory. Okay, so you are getting the expression of inductor. Directly it will be coming from here. You can cross check it. Okay, if you have faced any difficulties, you can ask me. So again I can discuss. Basically that is very basic idea. So that's why I am not mentioning here. So directly you will get from that expression. Okay. then you can make that saturation list for the short circuit. Okay. So previously you can see that the short circuited path, so you make it 0. Okay, then you can calculate what is the value of B sat. Okay. So magnetic circuit is there, length is L, MMF is F, area is AC. So your total MMF F equal to H into L, then series H equal to B by mu and B equal to phi by AC. We can express it as F equal to, you know that MMF L by mu AC into phi. Okay. Again reluctance R equal to L by mu into AC. Okay. So R equal to L by mu into AC. You know that formula. Okay. So it is a magnetic circuit. Okay, R equal to reluctance of the element and phi equal to total flux and F equal to what? F equal to mmf. Okay, so what you can observe from that study, that magnetic represent the each of the element with reluctance winding at the sources of the mmf. mmf is simplified in electrical circuit. It's known as a voltage. Flux is known as a current in electrical circuit. Solve the magnetic circuit using Kirchhoff laws. Okay, Kirchhoff laws. You know that one, that flux lines are adding, okay, multiple flux lines. So phi 1, you can get the incoming is phi 1, outgoing is phi 3 and phi 2. So phi 1 equal to phi 2 plus phi 3. You know that one with air gap calculations. Okay, all are there. Okay, so then you can use the Ampere circuit law, the total current passing through the interior of the path. So magnetic analogous to the Kirchhoff voltage law. So H into dl, okay, for the left hand side equals to sum of all the mmf. Okay, sum of all the mmf across the reluctance around the closed path. Okay. Right hand side equal to current in the winding are sources of mmf. Okay. And n turns winding carry the current IK. Is modeled as an mmf, means voltage source of value n into I into T. Okay, total mmf around the closed path add up to 0 value. Okay. Then we are using some of the air gap. Okay, that may cause for additional leakage. Okay, now you know that linkage as well as the leakage. So Ampere's laws are there, Fc plus Fg. It is for air gap, it is for core. Total mmf adding the n into I, so adding mmf. Okay, so I into Vt, n turns are there. Okay, cross sectional area, that is AC, here gap Lg, magnetic path length Lm. Okay, so core permeability mu C. Okay, so finally you have that equation. So both are adding in series. Now Rc means core reluctance, Rg means your air gap reluctance. Both are in series. Phi p is there. Okay, Rc equal to Lc by mu by AC, Rg equal to Lg by mu 0 plus AC. N equal to phi into reluctance of core plus reluctance of air gap. You can add that one. This is your air gap length Lg, cross sectional area AC. Now you can add both of them, replace that value Rc and Rg. You have that value, you can replace it. Okay. As per the Faraday's laws, you will get that induced EMF value Vt equal to n d phi dt. Okay. So Vt equal to again n square Rc by Rg into di dt. Okay. So hence the inductance is equal to L equal to n square by Rc plus Rg. Directly we are getting that value. So if you have the air gap, so you can see it is shifted. The linear, the saturation reach quite less. Okay. In I set 1, when you don't have any air gap, only core is there, only 1 by Rc means reluctance, only the core reluctance is there in denominator. In the case N2, here you can see denominator is more than your previous one. In that case, denominator value, the reluctance of the air gap is added. Okay, that may cause for reaching the saturation is quite less. So that's why when we are designing the inductor, okay, of the switching converter, we are adding there some of the air gap. Okay, in the core. Okay, some of the air gap for increasing the level of saturation. So okay, means Vsat by increasing the reaching probabilities of the saturation. If the air gap is very less, then what happens? It will be saturation will be earlier. Okay, if there is some area of air gap, length of air gap, so saturation will be less. So that's the motivation of the study. Okay. So if you make the more air gap, so that may cause for more leak. You have to moderate. Okay. So that you have to calculate. Okay. The calculation has to need to be done by yourself. Okay. So total expressions are there that is previously discussed, that N equal to phi into RC into RG plus RG. Okay, that is inductor expression. So saturation flux, okay, it has to be set into AC. So I said you can also calculate. Decrease the inductance. The effect of air gap is called decrease of inductance. Okay, increase saturation current. Okay, inductance is less dependency on the core current. So that's the effects of air gap. Okay. So in my next class, then transformers models also be discussed. Okay. So in the next class, I'll discuss on it. Okay. So transformers model. So till now, you can do for it for the inductor calculations. Okay. So actually, the time is I have there is a next time of the next class actually. That's why I need to stop. Okay. So if you have any queries, you can ask me. So I can repeat that one. But you can also text me in the chat box. Okay. So we can discuss it. Okay. So you can also take. You can also note it down in your homework copy. No, means classwork copy. So no problem. In next class, I can also rediscuss that question. Okay. Thank you. So today I can stop my session.